The bulk temperature, or the mean temperature, is very important in a lot of practical scenarios. And here we're going to look at a case where the bulk temperature is used to identify what the temperature evolution is downstream. The assumption is that we have a system with some sort of internal heat transfer processes where we model it with a heat transfer coefficient, and we may have, for example, a heat transfer coefficient on the outside. So let's understand this problem better. We have a flow through a channel, as shown to the left and shown in this drawing, where there is a resistance as provided by an internal heat transfer coefficient. I'm going to call it HI times the perimeter P, and so this is for some delta X region. If you wanted to, for example, we could say that this is a delta X thickness, so this is the area over which this occurs. And in general, we have some sort of conduction resistance, so you have a conduction resistance within the pipe, and then you might have, for example, some sort of heat transfer coefficient, or said differently, a resistance on the other side of this problem. We might denote that by HO, call this PO delta X, and so we'll call this PI. So the parameters are different. So PO would be 2 pi RO, whereas PI is 2 pi R sub I. Well, one of the interesting ways of solving problems like this, and so the problem that we're going to take a look at, is a case where there's some temperature out here at Tc, so this is some average temperature or reservoir temperature outside. And this is actually what I call TH out here. So this is TH outside, and there's some Tc, which is the bulk temperature within this pipe. So we have the other side of the pipe here, and again TH out here with some heat transfer coefficient HO. So what we might be interested in is understanding what the evolution of Tc is. And so we set up a local energy balance as shown here in this control volume analysis. So the control volume analysis says that we have an enthalpy flux in, enthalpy flux out, and we have some heat transfer in. So note here that we're using this idea of an overall heat transfer coefficient, often given by the symbol U. So U is the overall heat transfer coefficient, or effective heat transfer coefficient. And it's typically defined in terms of the resistances in the problem. By that, what I mean is that as we look at this series resistance system, you can imagine that there's a overall resistance. So take a look up here. There's an overall resistance in this problem, and I'm going to call that R total. That's equal to the sum of the resistances, the convective resistance inside, plus the convective resistance, plus the outside convective resistance. And if R, as an example, is defined in terms of the relationship between Q and delta T, so typically we think about, let me just start from a more physical perspective. We would think that Q, the total heat transfer rate, is equal to delta T over R, or R is delta T over Q, with units for R of Kelvin per watt. Now, oftentimes we will do problems where we have a Q prime, which is a heat transfer rate per unit length, in terms of what you might call an R prime, where R prime is defined in terms of R and the length scale. So R prime is R times the length. In this case for us, the length is delta X for this control volume. And then similarly, you can think about a Q double prime, which is the flux, which is delta T over, for example, R double prime, where R double prime can be thought of as R times the area. In this case, it's the perimeter times delta X. So it's equal to either, you can think about it as R prime P, or in terms of RP delta X. So U, the way we've defined it, is 1 over R double prime. Okay, so it's 1 over the resistance defined on a watts per meter squared Kelvin basis, or said differently, R double prime is meter squared Kelvin per watt. Okay, so using this idea of the overall heat transfer coefficient, we can define the area, the overall heat transfer coefficient in terms of the resistances and the temperature difference in that system. So the energy in is in terms of the Newton's law model for heat transfer in, the bulk flow through the X boundary condition, X boundary, and the bulk flow at dx plus delta X. As we've done before, we can take differences in temperature divided by delta X, and that's shown in this line. We do a limiting process of delta X going to 0. We come up with a differential equation for the bulk temperature within the channel in terms of the overall heat transfer coefficient, the perimeter, the mass flow rate, the specific heat capacity, and the temperature difference between the bulk inside and the bulk outside. And based upon this, we can solve this problem, and there's an easy solution when TH is constant. So constant cases of TH might be a saturated process. So if you had, for example, steam on the outside, even though there's heat transfer, there's no change in temperature. It's just a phase change process. If we say that the cold stream comes in at some T cold in, then we can set up an excess temperature, Tc minus Tsat. And in terms of this problem, our original problem in terms of dTc dx is in terms of d theta dx, and we get a separable solution. So really what we have here is d theta dx is equal to minus up over m dot cp theta. We divide by theta. So we get d theta over theta is equal to, and then multiplied by dx minus up over m dot cp dx. We integrate from theta 0 to theta and from x is equal to 0 to some x value. We get the log of theta over theta 0 is equal to minus upx over m dot c. And we raise everything, we exponentiate these things, and we get theta of x over theta 0 is equal to exponential minus upx over m dot c, which is the result that we show to the left here. So we have a recipe for Tc as a function of x in terms of the inlet temperature, the free stream temperature, and heat transfer coefficient based parameters, mass flow rate, and specific heat capacity.